Some of you have made it all the way to the end of this. Some of you are somewhere in the path, but Luke is going to show us how to solve this problem. It can't be any worse than mine. Try it again. There, yeah. All right, so what Luke's showing us is that in order to calculate the energy, we needed to have the frequency, but we were given the wavelength. So the first thing you need to do is convert the frequency convert the wavelength into frequency by using the C equals lambda F, okay? And so we rearrange that for frequency, and that becomes C divided by lambda stands in for F. So that's the first term in the equation here is just this is equal to the frequency, right? And then we multiply the frequency times Planck's constant to get the energy. But the energy that you're getting by doing that is for one atom, okay? Which is why it's so small. The number that you get is teeny tiny because it's just the energy for one electron to leave one atom. But what you're asked for in the question, it's asking you for the units. So I would recommend, as always, kind of coming back to this, when you're reading a question, whether it's in your study guide or in a test, that you annotate the question however you need to make sure that you have all the important things. I would definitely try to get in the habit of doing something to highlight the units that it's asking you for. If it ever asks you in a particular unit, or like if the question is asking for a electron configuration and it says condensed or full, that might be another thing to circle or highlight, just to make sure that you're, because it's so easy for our eyes to just pass over these things and not even take them in. I know, like, I'm a really fast reader, which means I can read a book like 5 times and still get something out of it because I got the gist of it the first time, but there's always little details that I just kind of glossed over in order to get to the plot. And so it's really easy to do that when you're answering these questions. So you had to multiply by Avogadro's number, and then because our Planck's constant is in joules, but we're being asked to give it in kilojoules, we had to do the divide by 1,000 in the end. Okay. If you are ever uncertain about something like this in terms of the units, in terms of where am I, you can always either write the equation out with the units in every part of it, or you can kind of write a little equation that just has the units, right? So I could say, all right, my E is going to be equal to H times C over lambda, right? So that H, Planck's constant, is in joules seconds, and C, is in meters seconds to the -1, right? And that's all on top. And on the bottom is my wavelength, which is being given in meters. This is another thing to pay attention to. The wavelength in this case was given in meters. They might give it to you in nanometers. Okay? How many nanometers are in a meter? So I couldn't quite hear what you said, but let's just say, so meters, decimeters is 1/10, right? So 0.1 meters, a centimeter, 0.01 millimeter, 0.001. A nanometer is times 10 to the -9th. Okay, so this would be times 10 to the -3rd, second, first. This is times 10 to the -9th. Okay, so just be careful that you're paying attention to the units that you're given and the units that are coming out. And actually that is in your data booklet, I believe. Is it in your data booklet? I feel like it is. Yeah. And you don't have to look at it right now, but in section 3 of your data booklet, right after the standard physical constants, you have the metric multipliers, the symbols, and the values. So if you're ever like, I don't remember if this many nanometers, whatever, you can find it in here. Now, what it doesn't tell you is things like cubic. So when we talk about decimeters cubed, you know, how many liters is that or whatever, like, or for how many centimeters cubed is that? Like, just make sure that if it's cubed, you're thinking about that as well. But hopefully you just kind of practice enough that becomes not a huge deal. Let's see, I'm just going to get rid of this part. So as far as this equation goes, I can immediately get rid of the I can get rid of the seconds and the seconds to the -1 because those are on the same side of the line, and they cancel each other out. This meter on top and this meter on the bottom cancels out, so your energy is going to be given to you in joules. Okay, so that you can always do something like that if you need to sort of double check your units, but you don't have to if you feel pretty confident about it. All right. Any questions on this? Okay. I want to point out, you can do number 4 on your own, but it's missing some very key information, which if you looked at number 4 and said, oh, I want to do this, you're missing the information that you need, which is the ionization energy for copper. So please, on number 4, please write that in. It's 745 kilojoules per mole. So make sure you have that written in under number 4 so that you can use that to practice another calculation with number 4. So that was an oops left out of the study guide in the PDF. Okay. So again, that's 745 kilojoules per mole for question 4. That's key information that you can't answer the question without. Now, you could actually, in your data booklet, now that I'm thinking about it, you could actually go to section 9 of your data booklet, and this has first ionization energy, electron affinity, and electronegativity of the elements. So it's one of the many periodic tables in your data booklet that has a bunch of info on it. Okay, and so you just read the graph. This here says 745 for copper. Okay, so you could have looked this up. You could have answered that if that was the test question by just looking it up. But knowing that it exists here is helpful. Okay. So I'm sorry, I had a class last night, so I haven't been able to post the videos and stuff from yesterday. I will do that today. Also, you will have a lab on Friday. Okay. Okay, so I believe this is page 8. Is it page 8? Am I correct about that? Yeah, okay. Okay, so why do we care about ionization energies? How does this help us understand electron configurations? Okay, so we'll talk about ionization energies again in the next topic, in the periodicity topic. But we can also use this to think about our electron configurations, okay? So everything that you learned in honors chemistry about ionization energy was technically about the first ionization energy. Possibly, unless you had Dr. Sorensen, in which case she might have run through some of the successive ones. But here, we're talking about one atom, and we're removing successive numbers of electrons. So we remove the first one, and it's a +1, and then we remove another one, now it's a +2, then we remove another one, now it's a +3, etc. So we can do this, at least in theory, all the way down to it has no electrons, okay? But what we see is we get what we call successive ionization energies. So we have the first ionization energy, second ionization energy, third, etc., fourth. And if we look at the patterns of those numbers, or if we look at it in graphical form, we can use that to identify an element, okay? Or at least identify what group an element is in. So if we look at this example, all right, this is sodium, okay? The first ionization energy is really low, okay? Now, there's no actual scale on here, and it's a log scale, okay? We have a pretty low number, which makes sense, because sodium is a metal, it's in group 1, it's going to be relatively easy to pick off that first electron, because if we're anthropomorphizing, sodium kind of wants to lose that electron. It wants to go back to the full octet state. So the amount of energy it takes to pick off that one electron is going to be pretty low. But the next electron, now we're picking off an electron out of a full second sublevel, right? So we've lost the 3s. We've lost the 3s1 electron. Now we're pulling the electron that comes after that, which means we're taking it away from being a full octet. Okay, we're saying, okay, you got the full octet, that's great. Now we're going to take another one. It really does not want to lose another one. So it's going to take us more energy to get rid of that second electron once we've already gotten rid of the first one. Okay, then if we go for the third electron, the fourth electron, fifth, sixth, seventh, eighth, then we're getting to, you can see that it's increasing, but it's not increasing by that big of a jump, right? But the next one, going from having 3 electrons to having 2 electrons, is also going to be a big jump, because again, we're going from I did that wrong. Going and getting rid of the second electron is, when we have 2 electrons, is another jump away from stability, because that's disrupting our full duet that we still have on those, what started out as core electrons for sodium, and what is now, if we remove all of these electrons first, getting rid of that full duet is also taking a lot of energy. And then getting rid of the last electron after that takes a lot of energy, but not that much more. So what we can see is that the large increases correspond to areas of where an element would be stable, and then we take another electron away. So we can use this to kind of figure out the electron configuration of an atom. So you won't have these labels on there, but you can see that removing the first electron, easy. Next one, really hard. That usually means it's in group 1. Okay, because first one was easy, Next one is breaking up the octet. Okay, and then if we go all the way through here, we can see, okay, this is losing the next 8 electrons, and then we have another jump, which is breaking up the full shell underneath it. Okay, so this is the kind of pattern you're going to look at to be able to figure out what kind of element this is. And it's also, seeing this is actually also evidence for these energy levels, right? The existence of these energy levels. It's really hard to remove that second one, but then all through the second energy level, even though there's slight differences in the S and the P energies, the main energy level too, it's increasing because it's increasingly harder to remove an electron because we still have all the protons sitting there, and that force of attraction is going to be, pretty strong. But there's not actually that much of a difference until we get to the next shell. Okay. So we're going to see an increase no matter what. It's going up. It's never going to go down in a graph like this, okay? Because we're continuously removing electrons. But the larger increase is telling us what group it is, okay? Questions? Yes. That's a great question, and this is where I understand why the NSJ Chem, who puts these together, did include some stuff on periodic trends in ionization energy. So for elements just by themselves, there are trends. If we look at, if we use p-table to look at first ionization energy, okay, we can see that energy, it gets harder and harder as we go across to remove that first electron, and then any successive ones are going to be higher than that, okay? But to remove the first electron for any of these is going to get harder as we go across, okay? It's going to get easier as we go down because those outer electrons that we're removing are farther away from the nucleus, okay? Now, in p-table, you've only ever been asked to look, if you use p-table at all, at just the baseline first ionization energy. If we put second, now we can see that second ionization energy is really high in group 1 because we've already lost 1 electron and they now have a full octet, right? But it's awfully low in group 2 for the second ionization energy because they've only lost 1 electron. They have 1 more in their current valence shell to lose. If we then go to the third ionization energy, now our group 2 does not want to lose an electron. Yes? Yes. Yes. So the blue is more energy, okay? So first is going to be, our blue is going to be here because the noble gases definitely don't want to lose an electron because they're perfect, okay? But as that perfection moves when we remove an electron from group 1, then our second ionization energy is going to be the highest. It's going to be the maximum in the period. And these guys will still have 1 more to lose in their S shell, their outer S shell. But as soon as we go to third, now these guys have lost both of their S electrons, and to take 1 more away is going to break up that full octet in the shell below. And so you can actually go through this and sort of, like Finn said, like watch it march across the table in a sense. That is a great question. I don't think... Yeah, the reverse of ionization energy is electron affinity, and p-table doesn't actually show you that. But you can kind of, and we'll talk about this later, you can kind of see similar trends in reverse for electron affinity. So good question. But we can't play with p-table that way. Okay. So you can see this in graphical form, but you can also see it in a table of numbers, and you might see either one or both on an exam, okay? So this is just showing us elements in period 3 going from sodium to sulfur, okay? So we've got our group number, we've got first ionization energy, second ionization energy, so the little subscript is what we're paying attention to, third, fourth, fifth, sixth, seventh, etc. Okay? So how hard is it to remove that first electron? We can see that as we go across the table, so this is, going from group 1 to group 16, we're seeing an increase in that ionization energy. If we look at the jump, the difference between the ionization energies, for sodium, we're looking at a 10-fold difference when we get to ionization energy 2. And that tells you that that is where the octet is breaking. Okay? So, and they're sort of bolded in your sheet. I don't know if it came across, but what you should sort of see here is a line that says, okay, for sodium, it's easy to remove 1, really hard to remove 2. Yeah?
Is the second level of ionization energy about removing 2
Yes.
the second
Okay, great question. It's about removing the second electron after the first one has already been removed. Great question, and that's going to come up in a minute. We're 50, okay. So we're assuming that we already have lost 1, and now we're losing a second one. That's breaking the octet for sodium. But for magnesium, losing the first one, yeah, it's a little higher. It kind of wants that electron. It's higher if we go to the second ionization energy, but then all of a sudden we jump to 7,000 for the third. So that means it was relatively easy to pick off 2 electrons, and then it got way, way, way harder. So the place where it gets way, way, way harder is where the octet has to break. Okay. All right. So you can see a pattern like this, and that means that you can be given one row of this table without the element being signified. You can just get, without the element in the group, they can give you successive ionization energies in a table, and you have to figure out which group it belongs to. Okay? So you may be given it in graph form, you may be given it in table form. So if we look at this graph, this is typo. It's just one element. It says elements. It's just one element. And you can tell that because we'll be looking at graphs where we're looking at different, out by atomic number, looking at different elements, but number of electrons removed means this is successive for one element. Okay, so where do we think this element is located? What group do you think? It can be any period. We don't know for sure what period it is. They're not going to give you period 1. Yeah. Okay, why do you say that? So this is removal of the first electron, okay? So 0 is the neutral, okay? Yeah. So, yeah, so this is probably going to be group 13, okay? If you say group 3, I don't know if they would give you partial credit. This would probably be a 1-point question, so probably not. Because remember, group 3 is in the transition metals, and things get wonky there. So they won't give you a choice of groups 3 through 10 if it's a multiple choice question. If it's not a multiple choice question, just mentally block those out, okay? Here's another one. Yeah. How come it's not group 3? Well, okay. It's not group, well, so it has to do with the length of this, and we're going to talk a little bit more later about the transition metals. So this is 8 electrons long. So we lost 3, and then losing 8 was the next chunk. So, you know, if this is actually number of electrons removed, we could actually also tell which, you know, potentially which period this belongs to. Yeah. Yep. Yes. Yep. Right, because boron doesn't have this many electrons. Yes, exactly. So it's not only group 13, it's also aluminum. Okay. Yes.
Are there graphs like this for like the transition?
Yes, and we're going to get to those later. Yep. Or sort of like this. Yeah. Well, we'll talk specifically about the transition metals in a bit. Okay. So we can look at another graph. I'm not going to go over this one. You can check it. I promise I will post the answer key in a little bit, but this afternoon for sure. But this is another example of how you would get a table problem. Okay. So number 4 says, explain to which group the element belongs. This would be, explain would be like a paper 2 question. You'd have to like write something out, okay? Not like a whole paragraph, but you'd have to do it in writing. You might see the same thing in a multiple choice question where it gives you group options, okay? So where do you guys see the biggest jump in this table? Yeah. Which one? The 5th one, yeah. So going from here to here is a huge difference. We're like 5 times higher energy, okay? So that means that we can lose 4, and then it's really hard to lose the 5th one, okay? So what group would this be? So we can, where's the thing? So we can lose 4, which means we're losing the S, and then we're losing 2 P's, or really the other way around. And then as soon as we lose more than that, we're breaking the octet. So I like to think of it as, okay, here's where the octet broke, okay, and then there were 4 more electrons, so that is going to be group 14 that were lost before we broke the octet. Does that make sense? No. It's hard to wrap your brain around. Yes, and so feel free to draw yourself a little table. If this is paper 2 question, if you have extra time and you're not sure, draw yourself a little graph. You can do that. It's not like there's a scale on the y-axis anyway. You might also be asked to draw a graph on an exam question. Okay, so this would also be, see, it's starting at 1, so your number, this one starting at 1 would be something not 0, and then it's just the relative number. So you would have to make sure if you're drawing a graph that numbers go up, and that you can detect the gap, the big jump, okay? But where exactly you put the dots doesn't really matter. Okay. I had an extra practice question, but I think what I'm going to do is just hand out homework for tonight, which is actually on the the previous stuff. And I know, if you've got a lot going on, do it when you can. And we'll go over it first thing tomorrow.